Good evening, everyone, or good morning, or good afternoon. I guess it depends on when you'll be watching this webinar. But my name is Dr. Paul Riccomini, and I would like to welcome you to DLD at Night 2021. It's a reboot of our original DLD at Night that was postponed. And again, it was adjusted for the current situation. But I'm very excited to have the opportunity to present to you on a very important topic that my work with schools and teachers shows that it is a very challenging and problematic area for teachers and students. And that is this idea of retention. So my session will present a strategy that will allow you to optimize practice opportunities in mathematics to help students with dyscalculia retain important essential concepts and skills. So one of the things that is important in math, as math teachers know, is not only that kids are learning new content, but they're also remembering what they had previously learned. So this strategy, I kind of put it into an umbrella category of high intensity instructional techniques for math. So sort of a play on the CrossFit world out there. But in tonight's session, I'm going to sort of take you through this particular technique, and our general, our big idea is like, how can we design instruction activities that are helping students achieve at all levels, but in particular, those that are struggling and have learning disabilities. But I think it's important to note that this strategy can be beneficial to all students, regardless of disability or ability. But before we get into that, it's important that we learn and sort of talk about this idea of this cognitive process that's involved with retention. I think it'll help teachers understand better where and how to use this particular technique. Now, the technique we're going to be learning today is called interleaving practice format, or I like to call it IPF. I mean, in our profession, we have to have an acronym for everything. That way we have our secret code. But interleaving practice format is a specialized practice that really is focused on helping students retain what they have learned. So I need to kind of set the parameters here. This is not going to help kids learn new content. This is going to help kids remember what they have learned. So I think it's important that we note when a strategy should be used. Now, before we get into the strategy, I want to lay some background and some sort of foundational pieces here. So we're talking about retention. So retention is defined as long-term learning. So it's not reviewing something so that they can pass a test. This is really designed to systematically promote, enhance, support the remembering of content across time. Now, in mathematics in particular, our content is especially susceptible to retention issues. So our content is very much interconnected. It builds upon itself. If you think broadly, we start off with whole numbers, we expand whole numbers into rational numbers, we take rational numbers and expand it into ratios and proportions. We expand that into the sort of the linear coordinate system, and it's just a constant expansion. So I don't have to tell practicing teachers out there, when kids can't remember, or sometimes what we call gaps, it creates issues. And those issues only get more problematic as kids progress through their program. So I'm going to boil down what we do and completely oversimplify it. But I guess teachers are used to that, into two words in terms of what we do: in and out. So if you kind of think about what you do on a daily basis, you are either putting information in or you're taking information out. We today are focused on the out. So we spend the majority of our time putting information in. So if you ever kind of had that tension of, geez, I have X amount of content to cover in X amount of days, I need to move. That's that in piece and that tension that's created. The out piece are things that you do to help kids take information out. Now, it's not that we don't do that. It's that the way we do it is often in a testing situation. So a lot of times when we're taking information out, we're giving them a quiz, a test, an exam, end of year assessment, and it's about out. So what we're going to focus in is on the out, but it is in a non-evaluative exercise. So I want to make that very, very clear that this technique is not designed to be used as an evaluation. Now, you will get a lot of good information as kids do this technique, but it's not really designed as an assessment, and it's designed as an exercise that promotes a cognitive process that results in more durable learning. In other words, learning that lasts. So a couple of guiding questions that I like to sort of put forth with this. Is retention a major challenge for you and your students? Now, if I could see you, I'm sure you're shaking your heads. One thing that I have noticed working with schools and teachers across the country is if there's anything that math teachers agree with, elementary, middle, and high school, it's that retention is this constant challenge. And what I mean by that, have you ever experienced the sort of the phenomena where you're teaching something, you're excited about it, your kids are excited, they're into it, they learn, you give them a little check, they got it, you give them a test, they get it, and then a month later, that topic comes up in another sort of related unit, and the kids look at you like you are from Mars, and they will swear, you have never taught us this. That is what we are talking about, is this idea of after they've learned it the initial time, we need to help them keep it accessible. In other words, long-term retention. And that's when we start pulling our hair. We start losing our hair. Our hair starts turning colors, or it starts falling out, because you literally saw your students do the skill or concept accurately, understand it, explain it, and now a month later, it's like you never taught it. And that is this frustration that teachers are going through. This is kind of like our arch enemy. Well, when you kind of think about the learners that we're dealing with, obviously we have labels. Our particular field is label crazy, but labels don't necessarily help us instructionally. What we got to look at are the learner characteristics. And if you think about kind of filtering out the labels and looking at the learner, we have two kinds of kids. We have what I call strategic learners. Now, I'm not going to read the bullet here. You can look at it, but essentially, to boil down this list, strategic learners, they're the ones you want to hug. And I honestly mean that. They're the ones that you're teaching and they make the connection. They have the aha moment, if you will. The light bulb comes on and you can see it happening. These kids are just ready to learn. A great example of a strategic learner is when they will stop you mid-instruction and say, wait a second, I don't understand. So that's the first clue, is that they are regulating their learning and they know they're having an issue. Second is they ask you a question. The third is you say, wait a second, can you tell me what you don't understand? They can actually tell you what they don't understand. Where you have this other type of learner, which is non-strategic. And when they're confused and you say, tell me what you don't understand, they say everything. They look at you like, what day is this? Are you in math? They're just lost. So these non-strategic learners, they're approaching things unorganized. They can't break down the tasks. They can't focus. They lack persistence. They get frustrated. They give up easily. What is really relevant for our strategy is this piece right here, this idea of exhibits problems with memory. So we have short-term memory and we have long-term memory. we are kind of focusing on the long-term memory, but this is really, really important for the teacher to understand so they can see the context of this particular strategy to know where and when to use it. So if you kind of think about our learning process, again, we have this short term and we have this long term. So I really, really like this diagram because it kind of is illustrating cognitively what we can't see. So when we do that in piece, if you remember, that means we're putting information in through the kids' senses. So if you think about senses, we're talking about visual, auditory, touching, if they're using some kind of manipulatives. Then you also have taste and smell. Most of the time, taste and smell is not involved in math, maybe science, home economics, cooking, things of that nature. But once the information is inputted, it moves into this working memory, short-term memory part of the brain. And this is where the processing is taking place. If you know the analogy of like, this is the oven where the cookies are made. So in other words, in this part of the brain, this is where they're processing that new information that was just inputted. They're pulling previous knowledge, previous experiences, language, maybe some pre-skills that you prepped. And in that working memory, they're starting to learn. So they're starting to grasp, acquire the information. As they learn it, they move it to long term. And that the fancy name for learning is called encoding. So they're encoding the information into the long-term part of the brain. This is where information is housed. Short-term memory is limited. It cannot house information for long periods of time, but it moves it into long-term memory. So this strategy and all retention strategies are really trying to address the long-term memory. In other words, the information that has been encoded, we're wanting kids to have it accessible. If it's not accessible, then they can't retrieve it, and therefore they can't use it. So I want to make it very clear that some strategies focus on the working memory aspect, some on the inputting, the registry part. Our strategy is specifically taking a part of the brain and a cognitive process to try to keep that information accessible. When it's not accessible, then it does us no good. All right, so that's kind of the cognitive piece here. So this strategy is specifically setting up an activity that is going to leverage a cognitive process that strengthens the long-term memory. So there's this tension of kids forgetting and not remembering can be sort of described on this graph here that's called the forgetting curve. I know that I was not aware of this forgetting curve. Most teachers are not aware of it. We tend to be in tune to what I call the learning curve, which is the reflection of this graph. If you're all math, you know what I'm talking about, but that's this side. So how long does it takes kids to learn a particular concept or skill? That's where we're into. This forgetting curve is how quickly they forget it, or what's called learning decay. So anytime you learn something, once you get past the initial learning phase and it becomes encoded, it will begin to decay, especially if you're not using it. And that learning decay happens much faster than most of us realize. So as the learning decay occurs, this information is no longer accessible to students. When it's not accessible, then they can't leverage it to learn other concepts or skills that may build upon it. So this learning decay is our enemy as a math teacher, actually as any teacher. Now, just a couple of things to keep in mind here. Not everything will have this forgetting curve as steep as it is in this graph if it's something that once they learn it, they will constantly use it. So there are some things in math, once you learn it, you're using it from that point forward. There are other things in math that you spend like a solid unit on it, and then you move away from it and you're never using it. That's where the learning decay is going to really hit. But what you can see in this graph, in as little as 10 days, kids can lose up to 80% of what they have learned. So this is happening much faster than we realize. We have to really design some purposeful practice to try to reduce the slope. And then this is even more problematic for our kiddos that have disabilities, dyscalculia, because they may not be getting up here to this 90, 100%. They're already down here, which means when they lose information, they're losing it from a much smaller quantity, and it creates challenges. So the purpose of this strategy is to promote retention by trying to flatten the curve. I know I should have trademarked that phrase prior to the 2019, March 2019, because 2020, because I was using it way before that. But this idea of flatten the curve is really what we're trying to do with this strategy. Now, it'd be great if we could just totally flatten it, but that's not reality. Reality is this decay is going to happen naturally. What we're trying to do is enhance and support the retention to kind of lessen the decay. So again, even if we lessen it just a little bit, this is a huge amount of information that they now have accessible. So the entire purpose of this strategy is to flatten the curve so that information is accessible and durable. So that's the key. So when you're thinking about any type of activity in your classroom, and the purpose is retention long-term, then we need to do some very specific elements to help that come into reality. Now, you already are doing things that we as math teachers have traditionally done to promote retention. Now, here's where we don't use the word retention. We tend to use the word reviewing. But I want us to stop using that word reviewing per se, because reviewing does not necessarily mean long-term retention. If you review the day before a test, then your purpose of that review is really to help the kids pass the test the next day. That type of review is going to give us a short bump, but then the forgetting curve is going to kick in. So what I want you to do is just sort of take a minute here and start thinking about what activities you do or you see in math class that is promoting or designed to address retention, though we usually call it review. So take a minute. I'm going to pause myself here. You can pause the video, take a minute and jot down some ideas. Now, as you're jotting down some ideas about the activities you do, and trust me, if you are a math teacher in a classroom at any level, you do things. The question is, are they working? So I know when I was teaching, I did these two common activities. One of them was called here on the left, hope and pray. Please don't forget this. Please, please, please. The other one that I found myself doing a lot back then was, the ribbon around the finger. Don't forget this. I'm pretty sure when I said the words "don't forget," that automatically erased everything that I was talking about. So we have these pieces, but I haven't been in your classroom, but in general, my experience working with schools is these are the things that we're doing still. So pretty much starting in 5th grade and on, there's something called an opener, a warm-up, a do now, starter. The districts have their own names for it, but essentially it's a couple of problems on the board that had been taught previously. The kids come in, they have 5 minutes to work on them. The teacher's checking attendance, maybe checking homework, getting settled. Then the teacher goes over them. So you got that, typical. You have review days. So very common, hey, today's Friday, we're going to do review day, and there's some type of activity set up. Sometimes teachers use games. the old school Jeopardy, station centers, game-like activities, Quizlets, any of those kinds of things. Then we have maybe some cumulative review. So a lot of core math programs will have cumulative review pages, cumulative review problems. Maybe you do some test prep. You have kids taking the ACT as part of their assessments. They prep them on the AC, but then there's also computer practice. Now, I'm sure you may have a few other activities that I don't have, but these are pretty much the core that I see continuing today. This is what we're doing. Now, there's nothing wrong with those activities. However, if those activities were really accomplishing what we wanted, we would not be so frustrated with our kids' lack of retention. So what we will have to remember is these activities are what I call typical instruction. In other words, when I was a teacher 2 decades ago, I did most of these activities. When I was a student 3 decades ago, I was doing these activities. And our review / retention activities have not evolved, have not updated. We need a massive update, like your computer, your phone, we need an update because the activities we're doing have not evolved with the science of retention. So I call these, what we're doing are the Model T car, and the first generation cell phone, the big giant phone that you kept in a bag. Where there's some other techniques that I want to call the Teslas and the iPhones of the world of retention. They have been upgraded, specially designed types of activities that are very, very good at promoting retention. So that's what we want to kind of focus on. Now, before we get into the strategy, I also want to kind of set some tone on a couple other things. So we're in this world of data, almost too much data. It's almost paralysis by analysis. We've got data up to our ears. And when teachers look at data, we tend to immediately default to this idea if there's a deficit showing in the data, it's because they didn't learn it. In other words, it's an initial learning issue. And as soon as we default to that mindset, then we start thinking reteaching, new lessons, pulling kids out, tier 2 potentially, extra time. Even sometimes we start re-looking at our curriculum. But what we got to realize is some of that deficit data has nothing to do with the kids' initial learning. In other words, you did a really good job initially. We haven't done what is necessary to keep it accessible. In other words, long-term learning. So learning without retention is pointless. And I want to make that clear. It almost does not matter how well kids learn something the first time or in the unit or the chapter or in the moment if they can't retain it. It is literally pointless. I know that sounds kind of weird. The second thing is if you're in a grade level that's evaluated, and that's in most states, that's grades 3 and up. We are not really being evaluated on what we teach students. We are being evaluated on what our students are able to remember. Again, initial versus retention. And this is kind of important that teachers begin to recognize the importance of retention. So as we move into the strategy, one of the big things that I really want teachers to begin to sort of explicitly monitor or acknowledge is this idea of purpose. So this is a practice strategy. So anytime that you're going to give kids practice in math, what you need to think about is what is the purpose of that practice? And this is where matching the retention or the practice technique with the purpose is critical. So One purpose of practice is obviously in the initial learning. So kids have never learned, didn't know something, you teach it, you want to give them practice so they can acquire the skill. Practice in that stage is very slow. Kids need a lot of your support, prompting, guidance. They make lots of errors. And the focus is for them to just acquire the skill or concept. The second sort of purpose is this idea of retention. So now you say something like, okay, I'm going to do a practice activity today. It's on these 3 skills that they have learned. So the purpose of this is for the kids to retain it. All right. So you see the difference? Initially to acquire, now I want them to retain it. And this is what we're going to be zeroing in on in today's strategy. Now, there's also a purpose of fluency or automaticity as well as generalization. We are talking about these 2 right here. And what we have learned is practice for acquisition and practice for retention should look different, and they don't. Now, I'm saying they don't. Obviously, I probably haven't been in your classroom, but I have enough experience in seeing what's happening now is that there is not a difference between initial practice and retention practice. And that's what we're going to look at. So this is the key. If you say today's activity is a practice that is designed for retention, not review, but retention, then that's going to set in motion this strategy. And this strategy is called interleaving practice format. So we're going to talk about initial practice, retention practice, and what that should look like from a structural design framework. So if you are watching this video, watching this webinar, and you happen to have some math worksheets in front of you or your books in front of you, like pull that out real quick. Find some practice sheet that you gave the kids or exercise and look at the sequence. So what I'm wanting you to focus on is the structure. In other words, how is it organized? In other words, what's problem 1? What's problem 2? What's problem 3? So what is the student doing in your exercise? All right, so that's what I kind of want you to zero in on. We're not looking at difficulty levels of the problem, whether it's a word problem or it's a diagram. What I want you to look at is what is the kid doing in problem 1? What is the kid doing in problem 2? What is the kid doing in problem 3, and so forth. And if you look at that, you're going to see a structure. And so this is what I'm talking about with this strategy is sort of digging into the weeds of the practice. So I'm not concerned about 10 problems, 15, 20, 30, whatever. That's not what I'm talking about. What is problem 1? What is problem 2? What is problem 3? What is problem 4, etc.? What do they look like? And if you study that, you will see a structure. I guarantee it. And the most common structure that you're going to see is what is called blocked practice, or sometimes it's mass practice. So if you look at my diagram over here, block practice is when the problems are clustered together so that the students are practicing the same type of problem consecutively. So my diagram, you have 4 red problems. They're all the same. So maybe that's order of operation. Then you have these orange problems. Maybe that's calculating the area of a figure. Then you have these yellow problems. Maybe that's dealing with a word problem related to, I don't know, interest that you earn in a bank account. Then you have the green problems, and those are problems involving multiplying with decimals. So what's happening is the kids from problem 1 to problem 2 to 3 to 4 is doing the same type of problem. Block practice. Now, if it's an entire page of the same, so it's 20 problems of order operation, that's more massed. So we've got block practice is when the kids practice the same problem consecutively. What you want to recognize about this type of practice structure is its purpose. That purpose of block practice is it promotes initial acquisition of understanding and accuracy. So when you teach something new, the practice that follows that should be blocked. This is very important, especially with kids that have disabilities or are kind of slow learners. They absolutely need to have block practice. But here's the catch-22 with this. Block practice produces no, and I mean no, long-term benefit. So if all you're doing is blocked practice, or I should say you're doing all that the students are doing are block practice, you will not promote long-term learning. A recent study showed that 90% of all practice in programs is blocked. I obviously don't see all the programs that are out there, but I see a good chunk of programs, and the 5 most popular programs are all blocked practice. Block practice will produce a learning kit. Okay, so in other words, what's going to happen is block practice, excuse my sort of rudimentary drawing skills here, it will produce your learning curve where you take kids up here. If we give them a quiz or a test up here, it's going to look like they learned it. The problem is the forgetting curve kicks in and they lose it. So then we're feeling pressured that, oh, they forgot it. I need to do some more practice. So we give them more block practice. We get a little bit of a bump, but then we lose it. Then we do some more and we lose it. We do it some more and we lose it. So we're spinning our wheels because of the structure that we're giving kids to practice in math. So we're not going to get rid of block practice because it's important, but we can't have all block practice or we will not help kids retain information. So here's an example of block practice. Now I just pulled this from some schools and teachers that I'm working with. So if we look here at this practice, we've got 3 different kinds of problems. We've got least common multiple, we got multiplying with zeros, and we got standard form. But they're grouped together. So the kids will do 3 least common multiple problems, 3 multiplying with zeros, and 3 standard form. So even though that's 3 different skills, they are blocked because they are consecutively. 1, 2, 3, they're the same. 1, 2, 3, they're the same. 1, 2, 3. Well, the cognitive process that produces gives us a short-term gain, and not a long-term gain. Here's another one. I just took this out of a program. This is called Math Mixed. So this program is saying, hey, this is mixed review. So that means it's been learned. Now we're reviewing it. But if you look at how it's sequenced, there's 5 addition problems, 5 subtraction problems. Then in this one, they have to do factors, prime or composite, factors, prime and composite. So you can see here, it's blocked. What you got to recognize is this will give us a short-term bump, but no long-term benefit. So you do this the day before the test, you test the kids, it's going to look like they have learned it. The issue is they're not retaining it. So here's just another example here. And you know, I could open up any textbook and this is what it's going to look like. So in this particular one, check for understanding. So they're obviously focusing on division. So we look at it. Well, it's blocked because there's 6 problems, all division, blocked. So it's the same process. Then we've got word problems that are all kind of the same piece. So what you got to recognize is this isn't bad. It's the purpose of this is acquisition or a short-term gain, not long-term. Again, it is not bad. It's just not going to help long-term. And learning without retention is useless. Here's another example. And again, find any worksheet generated out or any free worksheet out there, they're all looking like these problems, or most of them. This is what I would call more mass practice because it's an entire page, 10 problems, all of the same problem type. Now, some teachers, don't be fooled by this. Some teachers will say, no, wait a second, this problem is different than this problem because this problem has grouping symbols. Don't be fooled by that. The process that is used to solve this problem and this problem is the same, and it's right at the top of the page. Kids are taught to look at this problem. Are there any parentheses? Nope. Are there any exponents? Nope. All right, then I have to multiply, divide, and so forth. Well, here's the process at problem 6. Are there any parentheses? Yes. I have to do what's in the parentheses. Are there exponents? Nope. Multiply, divide? Nope. Add and subtract? Yes, and so forth. Same process. Don't be fooled by the appearance. So again, this is blocked practice, and this will help with initial acquisition or give us a short boost that then falls rapidly. A colleague and I have coined this the bored brain syndrome. When you block, your brain will eventually become bored and you're no longer processing the problems, you're regurgitating them. That regurgitation will show a short increase that does not last. When I came into this research about 10 years ago and started thinking about how I used to present my students' math practice, it really dawned on me that maybe all of my practice when I was a teacher was blocked. So interleaving. Now take a look at my blocks there. Now my block colors are mixed up. So I've got a yellow next to a green, next to a red, next to a blue. So that is the interleaving. So the yellow block is order of operations. The green block is calculate the area. The red block is a word problem on interest. And the blue block is multiplying by decimals. So they're doing different problems in a row. All right, so that's the interleaving piece. So the key with this is that they're not ever doing 2 of the same problems in a row. So what we're looking for is this sequence of ABC, 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 or ABCD, ABCD, ABCD. So we're looking at 3 or 4 problem types that are put into this kind of sequence that are repeated 3 or 4 times for a total of 9 to 12 problems in this interleave format. It is this type of practice structure that produces retention. In other words, learning that lasts. So this is what is vital for retention. So it's not a either or. What you want to think about is block practice will get us up here where the skills acquired. So we want to block in this area, but once we get to this area, we want to do IPF so that it's maintained. Without the IPF practice, you get the forgetting curve. So it's not one or the other, it's the sort of the relation, it's the interconnectedness of blocked to the mixed or the IPF that we are trying to shoot for. And programs are overblocked and not anywhere near what we need for IPF. So the key here, this is a warning, is go back to your program, go back to your practice sheets, go back to your games, your study guides, your review days, and look at how you're giving those to the kids. My guess is they're predominantly blocked. Now, this is not like 20 different problems slapped on a page. There's a purposeful sort of strategic planning on the teacher's part. So your memory aiding device is a deck of cards being shuffled, mixing it up. We want to give kids mixed practice opportunities or IPF. where they are not practicing the same problem consecutively. So the cards are different. So here's an example. I took those, the least common multiple, the multiplying by zeros, and the standard form, and now I've mixed them up where the kid's going to have to do 3 different problems in a row. Least common multiple, multiply by zeros, standard form. And then that gets repeated 3 or 4 times. So they have between 9 to 12 problems. Now, it is this sequence that produces a cognitive exercise that produces durable learning. Now, we're going to talk about why, but this is what we're looking for. So here is another example, kind of an elementary example. So instead of having, 10 measurement problems, they have a measurement problem. Then they have a greater than or less than comparison problem. And then they have a basic addition problem. These are different. So the kids have to think, okay, I got to measure. What am I supposed to measure? This is centimeters. Here's the beginning, a ruler 0, and they measure it. All right, then they go here and go, okay, whoa, this is not a measurement problem. What am I doing here? Oh, I got to compare these, which is bigger. Okay, so yeah, 118 is larger, so I got to use the right symbol. All right, good. Then down here, solve. Okay, so I'm not comparing these 2 numbers. I'm not measuring. What am I doing? Oh, I'm adding, and then I have to add those numbers. So that cognitive process is what we know produces a much stronger long-term effect. And here's another example. And in my opinion, this is at all grade levels. K-12, we need to be doing this. K-12. So here in this case, there's sort of a place value, telling time, odd or even. Very different. Going to help us produce this retention effect. Here's another example. So we got some fraction problems, we got an expression, simplify, and we got a graphing. Those are dissimilar problems. So the kids are going to be like, okay, I have to add these fractions. Okay, they got unlike denominators. Okay, I have to do this. Then they're going to come over here and they're going to, oh, wait a second. There's no what is this? There's no fractions here. Oh, I got to simplify. Okay. And I got to do order of operations. So it's rebooting their thinking. Then they come over here and it's like, ooh, what? Okay, this isn't an expression. Okay, I got a plot. Oh yeah, so 4 and 6, plot, draw. So it's forcing them to think about each problem. So what you're wanting is this dissimilar sequence that repeats itself 9 to 12 times. Now, whenever I work with schools and teachers, all teachers start thinking worksheet. Got to do worksheet. This is how you do worksheet. No, you don't have to. I'll do an IPF with you right now. Now, obviously, this is the honor system. I can't see you. But if you're elementary level, do the problem that shows up in the green box. If you're upper, middle, high school, do the problem that shows up in the red box. So you're my students. And I pull out your dry erase boards. Hey, I'm going to put a problem on the board. You're going to do, all you got to do is write the answer down. These problems are going to be a little different. They're going to help us strengthen our retention. We're going to do this every once in a while. So, all right, class, here's your first problem. So, if you're in the green box, round that to the hundreds. If you're in the red box, factor the binomial. Kids write their answer down, hold up their dry erase board. I say, okay, everybody gets 600 or everybody got X times the quantity X plus 4. Hold them up. I'm scanning, checking. All right, great. Next problem. So now you see they went from rounding to what time is it? They went from factoring a binomial to a reciprocal. Totally different. All right, write your answer down. Show here how many got 130, how many got negative 1/3. I can see the answers. IPF, no worksheet. Here's another one. Odd or even. Solve for X. So this does not have to be in a worksheet. But what has to happen is the mixture of the problem types. So in this case, I mixed rounding, telling time, odd and even, factoring, binomial, reciprocal, and solve. So this is this mixture that just produces this boost, this durable piece, or what we call an attentive brain. So the kid's brain is firing for each problem. Now that firing, what is happening is they're going into their long-term part of the brain and they're retrieving the process to solve that problem. In other words, it is exercising the brain. It's a muscle, we're exercising it. Where block practice, there's no retrieving it. It's all in the short-term memory, just being housed because it's problem, same problem, same problem, same problem. They're just spinning their working memory and they're not getting this retrieval piece. So what you want to take away from this as you begin to think about your practice is what's the structure? So take a look. What we know is the IPF structure is what produces a more durable learning that lasts, that retention. And it's the intentional mixing. You can't just grab a bunch of problems and throw them together. It's intentionally mixing the problems to make sure that they're not practicing any of the same problems. Now, you have variability here, but I kind of like, I said earlier, a 3x3 or a 4x4. I would not go any larger than 4x4 because an IPF practice actually takes the kids longer to do because they have to think about each problem. Where blocking, you're just getting the regurgitating of the process. And it's not going to last. So if you do a bunch of blocking and then test the kids, you're going to be like, "Ooh, they got it." Then a month later, or a couple weeks later, you're going to, "Hey, let's do this." They're going to look at you like you've never taught it to them before. So that's the key with this. So, hopefully, you've been processing. Well, why does literally adjusting the sequence produce such a large effect on their retention? I've kind of answered this subtly as I've worked through here, the bored brain versus the attentive brain. But if you think about this, there's really two things that are happening. The mixing of the problems forces the student to think through each problem and retrieve the process. 20 problems of order of operation, there's no retrieving. Maybe the first problem is retrieved. After that, these are all order of operation, and they just stop thinking and start just doing. So when it's mixed, it forces the kids to retrieve out of their working memory. So that retrieval is keeping the information accessible and strengthening that accessibility. So that's the first thing for why it works. The second reason for why it works is it really accentuates the discrimination that is so critical in math. So mathematicians or people that are good at math, we look at a problem and we discriminate. In other words, we say, "Oh, this is this kind of problem." Then when we go to another problem, this is not that kind of problem. This is this kind of problem. So we've discriminated. Block practice, there's no discrimination. So kids will often apply the wrong process, or will apply a process to the wrong problem. So in other words, they do the process correctly. They just didn't need to do it on that problem. And therefore, it ends up being wrong. So those are the two kind of big takeaways here in terms of why this works. Is it forces the retrieval, and its structure enhances and promotes the discrimination, where block practice does neither. And there's been, quite a bit of studies. I want to see more studies. I want to see more grade levels. I want to see more cognitive profiles, more proficiency levels, and then more math. Like, what math should we be doing with this? But so far, the studies all are kind of showing us this same pattern where block practice gets you a decent initial boost, but it just falls through the floor as you get further away from that block practice. Now, I suppose you could just block everything thousands of times and we would keep them there, but you and I both know there is no time for block practice to the extent that we need it. Where the IPF really produces is attentive and it lasts. I mean, this is where we want. I mean, yeah, so they did 90% early on, but at the end of the year, they backed down to 20%. What good is that? Where these kids, they maybe didn't get as good as I wanted initially, but it's maintained. That's the key, durable learning. And this difference here is about 200%. So it's not just a little bit, it's a pretty big amount. So when you're looking at this kind of piece here, and these are all the things that we talked about, blocking does not require deeper thinking. Students are just, after the first problem, they're just blindly applying it. They're not thinking, they're not discriminating, they're not retrieving. Where IPF is really requiring retrieval, and it forces them to pay attention or to discriminate. So, a couple considerations here. And again, we're not getting rid of block practice. I don't want anyone to think, oh, that's it, no more block practice, especially for our kiddos with disabilities. They need focused and sufficient block practice time. But once they begin to acquire the skill, now it doesn't have to be 100%, it's probably got to be bigger than 50%. Some studies have it in the 60 to 70 range, but they have to have acquired the skill. Once they've acquired it to some level, you got to start thinking about mixing. That is a skill that we need to mix. A couple other things, the research also really clearly showed that kids prefer blocking. I mean, who's going to argue with a kid where I don't have to think versus I got to think through every problem? So they prefer blocking. Get ready for some resistance to the interleaving. So, how do you do this? So now that I've given you kind of the strategy in a nutshell, the next question is, okay, how do I take what I just learned and implement it in my classroom? So here's kind of the guidelines. The very first thing that has to happen is you got to identify your problem. So you have to map out your skills. So I like to do this by month. Map out your skills, list them out, skills and concepts. And then the next thing is, which ones are you going to group together? And the defining rule for grouping is the problems have to be dissimilar. If they are not dissimilar, then you're going to get a blocking effect and it's going to do no good for retention. Now, I kind of like this idea of 9 to 12 in this ABC format, but it doesn't have to absolutely be that format, but it cannot be two problems of the same type together. So in your documents, your handouts, I provided kind of this sort of map guide that you could use for planning. Feel free to adjust this however you need. But I have it by month. I try to have teachers think about IPF separate from units or chapter, because an IPF can cut across units, chapters. It could cut across grade levels, actually, if you wanted to. But the very first thing is I like to do this in grade level teams, or at the high school, like Algebra 1s do this, geometry and so forth. The grade level teams list out the skills. So once you list out your skills by month, whatever that might be, some months are more than others, then you start grouping them together, A, B, and a C, right? That is your IPF. Call it 1. Then pick a date that you're going to do that IPF. I kind of am recommending that you start a minimum of 2 to 3 times a month. I think once a week would even be better, but sort of, you have to play around. Now, if you said I'm going to do one of these every 9 weeks, I'd say that's probably not going to give you any real significant boost. So think about sort of, systemically putting it in and scheduling it in there. Now, when you make the problem, when you make these IPFs, you want to pay attention to the difficulty levels of the problems. Don't put 3 advanced problems on one IPF. You'll overload the kids. But at the same time, don't put 3 basic ones, but try to do a mix that's somewhere in these kinds of sequences. So moderate, basic, moderate, repeated 3 times, or basic, advanced, basic, or moderate, advanced. So pay attention to the difficulty levels so that you're not like jamming 3 very difficult ones on there. I also encourage a word problem to be in there, not 3 word problems by 3 or 9 word problems, but your A might be sort of a moderate calculation problem. Your B problem is your word problem. And then your C problem is another basic or moderate calculation. And then that would repeat. So there would be 3 word problems on this IPF, sandwiched between 3 moderate or basic problems. The key is dissimilar. So in full disclosure, this is probably the biggest gray area, is like, what is dissimilar? You just have to make sure, use your professional judgment. You just have to make sure that the problems are dissimilar. Now, for some kids, dissimilar means they're really different. For other kids, they're maybe a step or 2 or a process or 2 different, but you want to guard against blocking, because if the problems are too similar, you'll get a blocking effect, not the retention effect. Now, when to do this? So, I think a good target would be 2 to 3 times a month. Now, you can do it in class or out of class. Advantages and disadvantages with both. I actually prefer starting it in class. Now, the disadvantage of in class is you're using up your time. But I just want to flash back to what I said earlier. Initial learning without retention is pointless. We have to allocate some in-class time to an IPF retention strategy. You could technically do this on homework. The advantage is you're not using your time, but the disadvantage is, are the kids going to do it? Or is someone going to do it for them? Or worse, that they don't have help. So, that's your call of how you want to do it. Me personally, if I were a teacher, I would be doing it in class. I would set up a structure. If I'm an elementary teacher and I'm big in stations or centers, one of my centers is going to be an IPF center, and I'm going to have kids go there, and whatever the activity is, it's going to be mixed. Middle school and high school, I'd probably designate 20 minutes one day a week where we do some IPF practice, either worksheet on the board, maybe I can find a game, something like that. But when you do it is critical. Sometimes teachers, they give it on Monday and then they collect it on a Friday to kind of give kids some time. So, how you work it in, you obviously will have to make that decision. But if you're telling me retention is a challenge and you're saying, but I'm doing X, Y, and Z, and retention is still a challenge, then what X, Y, and Z isn't giving us what we need. We need to think about something different, and that enters that IPF. So I talked about ingredients. Do a little quiz here. We'll kind of do this as a group here. But here are the sort of the checklists for you planning IPF that are non-negotiable. So non-negotiable means it has to be this way or it's not going to work. So the first thing is I want a mixed sequence. Now, whether it's ABC, 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 or this ABC 4 times or ABCD 3 times, it has to be mixed. Now, it could be ABC, BCA, CBC. All right, as long as they're not consecutive, that's fine. Second, when I look at the problems, I should see clear dissimilarity between them. Develop these in sets of 9 to 12. You do not want an IPF with 30 or 40 problems. You shouldn't be doing block practice with that many problems. But remember, IPF takes longer to finish. Therefore, you have to guard against overwhelming the kids. So 9 to 12, high school teachers have to really be careful about the types of problems they put on an IPF. Minimum of 2 to 3 times a month. I'd say once a week would be ideal. And then I have to work this in here. We're not getting rid of block practice. We have to use block to acquire the skill. Once it's acquired, then we need to move to the IPF. Now, as far as like things that are completely up to you, you want to do at homework or in class, or maybe you can find some computer practice that does the mix, or is there a game? That's up to you. So again, what you have a lot of freedom with is how to implement it. Now, as far as, again, the key is dissimilar. There's no black and white spelled out, this problem and this problem and this problem should be together. You just have to make sure that they're dissimilar. All right, so again, our overall purpose of IPF is to slow the learning decay. And I hope that you are sort of really taking a deeper reflection into the practice that you're giving kids, not in terms of how much or when, but what does that practice look like? Blocked or interleaved? Blocked is going to give you that bored brain syndrome, where interleaved is going to give you this attentive brain that enhances the learning. All right, so I hope that, I know we are sort of a condensed time frame here. I wanted to make sure to be able to answer some questions that might come up, but hopefully I have developed some knowledge in terms of practice that will allow you to more critically examine how you're giving practice and sort of make a distinction. Am I doing blocked? Am I doing interleaved? And what is the purpose? The purpose will tell you which one you should be giving your students. But with that said, I want to thank you very much. And I want to give you one last resource. This website, retrievalpractice.org, is a phenomenal website. It has a lot of retention strategies. It has the IPF, and it has these really cool practice guides. So if you go here, look up their practice guides, potentially free resources. It's kind of changes, and I haven't kept up with it because it's changing, but look for the practice guide on interleaving to give you some more information, develop a little bit more depth of knowledge as you think about using this particular strategy. So hopefully, maybe we're going to transition now, and you'll have an opportunity to ask me some questions. So with that said, I want to thank everyone for attending the DLD at night session on optimizing practice in math.